In the previous video, we used the Newton Asset tool to create a robotic arm with 6 angular degrees of freedom and a gripper with 1 linear degree of freedom. To control the robot, we used an inverse dynamics effector. This effector calculates the internal joint torques required to reach a specified target position and orientation. While inverse dynamics is a powerful approach, it has some limitations. Gimbal lock. The algorithm assumes that all degrees of freedom are independent. However, in certain cases, 1 or more degrees of freedom may become a scaled value of another, leading to a loss of control. This issue is known as gimbal lock, and it is undesirable. Reachability constraints. Not all targets are physically reachable. The set of all reachable targets is known as the robot's workspace. Solving these issues. There are several ways to handle these limitations. Predefining a sequence of valid targets to ensure the robot moves within its workspace. Using a procedural trajectory generator to compute smooth and feasible motions. Reinforcement learning with simulation, a modern and popular approach. In this video, we will use a procedural script to define a sequence of steps for the robot to reach a target. However, this script will not account for obstacles. Building the user interface in Unreal Engine. We create a blueprint user interface, UI, using Unreal Engine's UI system. Since UI creation is a standard process, we won't cover it in detail here. If you need guidance, there are many online tutorials available. For this video, we have already created the robot model and the UI blueprint. We will now walk through the schematic and explain how it works. In the content browser, we create a user widget blueprint. We add 7 slider widgets, 1 for each degree of freedom. After designing the UI layout, we switch to Graph View to add scripting logic for each slider. Initially, we test each degree of freedom independently. We add an on-click event to store each slider's value in a corresponding float variable. On the Begin Play event, the robot spawns an instance of the UI and stores it in a local variable for later use. Next, it retrieves an array of cubes from the UI, identifying all objects of this type in the scene. It also fetches the target location, which is marked by a dummy shape, and stores it in the UI blueprint instance. On every Newton model update event, the script first checks if any of the robot's joints have hit a motion limit. Losing a degree of freedom is undesirable. If a limit is reached, the robot enters a recovery function, slightly adjusting the joint until it finds a position inside the robot workspace. Once recovered, the robot is free to move again. Side note, determining a robot's workspace is a complex problem. The technique mentioned above is a form of supervised learning and can be used to train a neural network to represent the robot's workspace. It can also be applied in reinforcement learning to generate efficient paths, as the method simplifies into the following algorithm. To move from target A to target B, the robot must create a trajectory. At each step, the robot has multiple possible moves. Steps leading to conflicts receive a penalty, while valid steps earn a partial reward. The step that successfully reaches the target receives the highest reward. This approach forms the foundation of policy gradient algorithms and can be used to develop smart robots, particularly for object-picking tasks. We will explore this topic further in upcoming videos. For now, we will stick to simpler methods. Next, the robot retrieves UI objects and updates the 6 degrees of freedom based on the slider values. The gripper's position is also collected and applied to the corresponding sliders. At this point, the blueprint is complete and we compile the project. We then move to the scene to test each slider independently. During the test, you'll notice that the effector tip remains in a relative stationary orientation while the rest of the robot moves. This demonstrates the difference between forward and inverse dynamics, where we calculate joint torques to achieve a target, and forward dynamics, where each simply satisfy its joint desired prom. We now implement 3 key functions. First, a random target assignment. A new on-click event is added to the UI. Using a sequence node, each of the 6 sliders is set to a random position. When compiled and tested, the robot should move to a random position and rotation while keeping the effector tip focused. Next, we add a moving to the next box in the array script. The robot moves toward the next available box that is not already in the target destination. All the scripting uses standard blueprint scripting nodes. The only caveat is obstacle avoidance consideration. Instead of moving directly to the target box, the robot first moves above the target to prevent collisions, e.g., when stacking boxes. The final adjustments are made manually using the sliders. Test the script in the scene. The final script moves the effector to the target destination. This function is similar to the previous one but focuses on a different target. Test the script again. In conclusion, with these scripts, we have created our first functional robotic system with a single dynamic chain. In the next video, we will build a more advanced model using multiple dynamic chains, but applying the same principles. Thank you for watching, and see you next time.